That's wonderful. So thanks so very much indeed for the kind invitation to this exciting quantum summit. It's great to be here today. I've been specifically asked by the organizers too, and it's my great pleasure to give like a kind of a snapshot of the state of affairs of one of the most pressing, if not the most pressing topic in modern quantum computing, namely that of quantum error correction and mitigation. And here's the thing. Now, the core idea of quantum computing is actually not such a new idea. Already in the 1980s, Feynman, Benny von Deutsch were contemplating what kinds of supercomputing would be conceivable if single quantum systems were the carriers of information. But the big splash came only like in the last 7 or 8 years when protagonists actually set out to build such devices to a reasonable scale, mostly driven by the US tech industry, but also by players in Germany, Europe, and in China. Surely, the machines we have are not quite full fault-tolerant quantum computers, but it does seem fair to say that the development of quantum circuits has been enormous in recent years. We've seen superconducting circuits with a couple of hundreds or even over 1,000 qubits. There have been results on neutral atom machines with cold atoms being shuttled around with qubit numbers in the hundreds. That's an exciting state of affairs and puts the question on the desk whether we can reasonably hope realistic quantum devices to provide some sort of speed up over classical computers. Well, in principle, the answer is of course yes. A few dozens of quantum algorithms are known with super polynomial, aka exponential advantages of quantum over classical. There's a bit of a mismatch, if I may say, in that only quite recently progress has been made with the same rigor and kind of pedantic mindset on applying quantum computers to problems in machine learning, combinatorial optimization, and simulation. I've spent a lot of time on these questions in the last years. I'm not speaking about that today, but that's for another Bitcom, or grab me later at a coffee break. I have quite a lot to say about this. So this is an exciting state of affairs, indeed, but there's one big showstopper, one core problem in all of this, which is how to deal with noise. Quantum noise is our #1 main enemy of the state, and this is no detail whatsoever. Say, yes, the quantum gates, the constituents are very good. The average gate fidelity, that's a figure of merit between 0 and 1. 1 is very good, is, say, 0.999 for entangling 2-qubit gates. That's pretty impressive and wonderful, but it may not quite be good enough for what we have in mind. In fact, one can even see that if you run a quantum circuit and don't do any quantum error correction, and you have n qubits, then all you have is a depth of the circuit that scales like the logarithm of the number of qubits. Of course, you can run a longer circuit if you want, but you can just as well not do it or chop it off or put in the birthday of your grandmother. Log depth is all you need, or all you have. No need for panicking. The glass is half full or half empty. The fine print depends on the numbers, but it's important to know that there's like fundamental obstructions in the absence of quantum error correction. So this is the point of the rest of the talk. The regime we are in today is NISQ, is the noisy intermediate scale quantum scale. John Preskill coined this term, well, some years ago. But where we really want to be, the jump we want to make, is that to the fault-tolerant application scale, where we can anticipate the applications in optimization, machine learning, simulation, and so on. And to achieve this, we have to do something about stuff. And error mitigation techniques effectively reduce noise levels, yes, but that's the point of the first part of the rest of the talk, by how much. And second, can quantum error correction help? Can we overcome the the major gap to fault tolerance and to this application scale that is the place where we want to be. But let's start with quantum error mitigation, and let's see where we are in a very sober fashion. So, see, we want to apply, I want to go into the lab and apply a quantum circuit. That was a joke. Never let the theorists into the lab. But someone is running a quantum circuit in principle, but that's not what's happening. Either way, whatever you do, there will be noise in the system in one way or the other. There's decoherence, quantum noise, fabrication failures. The quality is very high, but you will be implementing some approximate noisy circuit. Okay, that's good. That's quantum noise. How can you undo it? You can't. That's in the nature of quantum noise, that you cannot undo quantum noise. What you can do is you make it worse. You can add even more quantum noise at different noise levels, and then you can extrapolate to zero noise, largely on the level of classical post-processing, and then infer what the result would have been at zero noise levels. That's called zero noise extrapolation. It's one of a portfolio of ideas on quantum error mitigation that largely mitigate errors on the level of classical post-processing. Is very important. It used to be in the center of the IBM strategy. It's a very clever technique. But how far can this go? And that's a question we looked at in the last year. Asking the question, how many shots do you need to do? How many sample points do you need, experiments you need to run to estimate data for a given precision and with high probability? This slide is a little bit for the geeks. Apologies. The way we looked at it was to make it a statistical inference problem in terms of the circuit depth, the circuit width, and using ideas of multi-hypothesis testing. But this makes a lot of sense, because if you want to do error mitigation, the minimum thing you need to be able to do is, if you send in something, is that you need to find out at the output what you've sent in. If you can't do that, then you're in trouble. That gives you a bound. And then techniques come into play that I'm happy to say a lot more about than you want to hear. So the upshot of this is that this provides ultimate bounds of this type, and that's innocent looking, but this tells you that the number of experiments you need to do, the number of samples you need to take, scales like e to the power of system size, number of qubits, times the width of the circuit. And this is indeed a bound that's fundamental in worst case and exponentially stronger than any previously known obstruction. Again, that's innocent looking, but what it means is that there are strong obstructions against error mitigation for circuits the depth of which scales like the logarithm of the size. There's a mathematician's joke that log is upper bounded by 4. It's a pretty good joke if you think about this, but it takes a second. So this is basically constant. In other words, error correction, there's no need for panicking. Error correction mitigation is important, but it does not scale in the system size. So we got lots of phone calls from IBM on that day, but very respectful ones, no shouting. But I don't want to be too negative. Error mitigation can and must be done, but it's important to acknowledge that it does not scale in the most drastic of all senses, and it also does not work well for all circuits, which is usually like an invitation to think outside the box, meaning we have to think of intermediate things between mitigation and correction in a way. Which brings me to the second and last part on quantum error correction. Now, error correction is again a beautiful and again not a very new idea. If you want to be sure about data, you use redundancy. That's a very old idea. If you have an iPhone, you want to be sure, you put it onto the iCloud, on a couple of hard drives. I have a good story to tell for the next coffee break on this. This makes your data safe. You have a bit 0, you store it in 0, 0, 0. You have a bit 1, you store it in 1, 1, 1. That clearly protects you against bit flip errors with high probability. Good? So the core idea of the Paris code from the mid-80s, some of you were not born at that time, was to take 0 and encode it into 0, 0, 0, and 1 into 1, 1, 1. But that's innocent looking. But the point is that you have this encoding, and you can distinguish the settings of having no error, a bit flip error on the first qubit, on the second qubit, or on the third qubit, and you learn something about the error, but exactly and utterly nothing about the fragile quantum information that is being stored, and that would deteriorate if we would learn something about this. That's not quite quantum error correction, but almost. It gives you the core idea. The first codes came with the Steen code and the Shor code in the mid-90s, where you take k logical qubits, you encode them into n, painfully many sometimes, physical qubit at k at a distance. That's kind of a quality measure of the code. So you encode a bigger system so that you can do a measurement, and you will be able to learn about the error and you can also find a correction without learning anything about the information and stored, hence quantum error correction. In 2001, the most popular code was presented. That's the toric and surface code. That's the Volkswagen of the quantum error correcting codes. It's in the center of the German strategy of IBM, Google. It's like a code on a square lattice, the quality of which depends on the size of the lattice, roughly speaking. That was super exciting. People got excited. But then over the years, the excitement waned away a little bit. That's what people call the Middle Ages of quantum error correction. But just like in the real Middle Ages, of course, a lot happened, but people didn't talk so much about this. But the geeks still did interesting work. In particular was the hot question whether codes would exist that would be attractive in all possible parameters. Say that the number of logical qubits would scale linearly in the physical overhead, and also the distance would do so. I mean, that would be conceivable in principle. It was a crime story of the first league to find out whether this would happen. At the end, people did like some random coding ideas and quantum low density parity check QADPC codes that made it work. In the end, it was found it's mathematically speaking possible. That was a big success at that time. But the big impact, the big explosion came just within the last year or so, when, again, people did this in the lab. For example, there was this spectacular experiment just before Christmas last year when people took 48 logical qubits and encoded them into 280 physical cold atom Rydberg qubits, like storing them, shuttling them around with optical tweezers into like an active region, doing stuff, putting it back, all with a RAM, and running a quantum error-corrected baby algorithm on a cold atomic device like that. This was done in Harvard in the US, but there's also similar data shown or done by Emanuel Bloch in Munich or Garching. We closely collaborate with and support in their experiments. Also, quantum error correction means you take data, you measure, and then you understand what went wrong, and you have to have an algorithm that gives you a strategy of what to do, and then you correct. But this was not done once or twice, but in fact, 1 million times in real time on the chip. Had you asked me like 2 years ago whether this was possible, I would have said sure, but give it 10 more years. This was published just a couple of weeks ago, months ago actually. This is quite impressive. But at the same time, with the experimental explosion, there was also a theory explosion, because there's now lots of theoretical questions back on the desk, aka our desk, how to think about things. And this decoding problem is not an innocent problem whatsoever, because you take data and you have to, in real time, make clever choices of what to do and what action to take to correct the error on the chip. And you are better, faster than the quantum noise. That's pretty fast, because that's screwing up your chip in real time. And that's a kind of a challenge. In particular, there was this big challenge whether such decoders, as one say, would work for these QLDPC codes, which are good codes altogether. There was an open in computer science and mathematical challenge. And this we looked at sometime just recently, and we did find that these decoders do exist. One can find them, and one can find highly parallelizable decoders which decode stuff in chunk and they communicate in the right way to have the optimal scaling, and find good parallel decoders for these QLDPC codes that are presumably fast enough, so there's reasonable hope so that you're fast enough and faster than the errors that are being accumulated in the chip in real time. This was a result that was done in collaboration between Berlin and Munich with help from Edinburgh and Gothenburg in Sweden. Another point is, yes, we want to reduce the overheads, and that's my last technical slide, but there's other things that are major bottlenecks, which are the complicatedness of measurements. You say you have a code and you have to do 8-qubit measurements in one shot. Mathematically beautiful, but no way this can happen in a lab, or 4-qubit measurements. You have to break it down into pieces. And we understood that you can take complicated codes, like the color code, that's the sister of the toric code, or the brother, well, diverse, whatever, and you make measurements and you make schedules. You make ABC, 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 like little schedules, and all you do is do 2-qubit measurements at a time, and you can do this. You get in the same phase, but with simple measurements that you can do with present technology. The previous thing just came out a couple of days ago. This is like a couple of weeks ago, again in a collaboration between Munich and Berlin. That's a very strong collaboration, I should say, and with friends from Cologne, bringing quantum error correction closer to reality. Which 3 minutes brings me to the end of my presentation. So the regime we're in is an exciting one. We are in the noisy intermediate scale regime, yes, 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 but it seems fair to say that the development of quantum circuits in the last, I should say months, not years, was enormous. Quite unbelievable. In system size and quality, which is maybe even more important, a lot has happened. That's great, but where we want to go is to the fault-tolerant application scale, where we can hope to find algorithms in machine learning, in optimization, in simulation. That's where we want to go. That's the FAST regime, which is still away. We want to make the gap in one way or the other. There's 2 take-home messages. Take-home message number 1 is error mitigation is important. It's relatively cheap. It's somebody else's problem. It's largely a classical problem. It will not bring us to the scalable regime. It must be done. It's an add-on. It will never die out. It's there to stay, but it will not bring us to the other side. If we want to come to the other side, we have to think of error correction. Error correction is taking off and might well do the job of going there. So the term NISQ was coined by John Preskill, where he had this article on noisy intermediate scale quantum settings. We're just actually together writing up a new article on creating a footpath between the NISQ regime and the fault-tolerant application scale regime, step by step of what avenue we can take. I like to be careful and cautious as a scientist and not bullshit too much around. At the same time, it's important to kind of keep a path from the NISQ and the FAST regime. And in fact, I'm extremely optimistic about us making this big jump. And on this positive note, I thank you very much for your attention, and I'm looking forward to a question you might have now, or maybe later in the coffee break, also ask me about machine learning. Thanks for your attention.